So the stuff that we're going to be doing today is something called initial value problems. It's very, very similar to what we were doing yesterday, except the stuff that we were doing with the previous section of 4.9 were just general antiderivatives, and the mark of a general antiderivative is that it still has the plus c. So with the plus c, it's a general antiderivative. We can get a specific antiderivative if we have something called an initial condition. And so I'm going to walk you through this first problem, and you'll see just exactly what an initial condition is. It's something that allows us to see what c is, what the constant of integration actually is for that specific problem. Is it 2? Is it negative 10? What is it? So let's walk through this first problem, example 1. So solve the initial value problem. So what we have here is dy by dx equals 8x cubed plus 3x squared. So what they're saying is they're giving us the derivative and then giving us an initial condition. So if the derivative of y equals this, we can start with y equals and then write what the original function must have been. So 8x cubed. In order to get 8x cubed, we must have started with 2x to the 4th. You can always retest that. The 4 comes out front, multiplies by the 2, that'll give you 8. Power drops down to 3. And then plus 3x squared, the antiderivative of 3x squared is just an x cubed. And then of course we start off with our plus c. Okay, so that's something called the general antiderivative. And remember, the general antiderivative contains the plus c still. And then they give us this thing called the initial condition. And this initial condition says, okay, if you plug 2 into the function, what you get is 0. And so you're plugging in a value for you're plugging in a value for x, you're plugging in a value for y, and that's going to allow you to solve for c. So that's how we do that. So the value they're giving us for y is 0. So we do 0 equals, and then we plug in 2 for x. Okay, and then when all's said and done, we'll be able to solve for c. So 2 times 2 to the 4th, that's the same as 2 to the 5th. So that's 32, and then plus 8. So 32 plus 8 is 40. So if we solve for c, of course, we'd end up with c equals negative 40. So by solving this, we get c equals negative 40, and then what we do is we rewrite our equation that we had right here, but we replace the c. So 2x to the 4th plus x cubed, and then minus 40. So what this equation is, it's an equation that has this as a derivative, but also if you plug in 2, you get 0. So kind of two different qualifications that we have to meet. All right, so we're doing pretty much the same thing for all of these problems. Some of them are just f of x, f prime of x, and then some of them are initial value problems with like particle motion, position, velocity, acceleration, and that's what we're looking at with example 2. So it says a particle moves along the x-axis with this function as its velocity. All right, 6t squared minus t, and that's given in meters per second. Find the position assuming that, and then it gives you an initial position. So to go from position to velocity, we take the derivative. So to go from velocity back to position, we take the antiderivative. So we start with, s of t equals, this is going to be the general antiderivative. So the antiderivative of 6t cubed, or 6t squared is 2t cubed, and then minus the antiderivative of t. Power pops up to 2, and then we divide by 2. And then, of course, we have a plus c. Then it gives us this initial condition. This is assuming the particle was at 4 meters at time t equals 2. So we plug in 4 meters for the position, and then plug in t equals 2. Okay, then we're going to simplify this right-hand side down. So 2 times 2 cubed, that's 2 times 8, that's 16. And then minus 1/2 times 4, of course, is 2. So we get 4 equals 16 minus 2 is 14 plus c. Okay, so c must be a negative 10. So then again, we start with that position function that we wrote. And instead of just a generic c, we are going to plug in the negative 10. So this position function specifically, this position function has this velocity function, which you could check just by taking the derivative, but it also meets this initial condition. Okay, now with example 3, we're going to do it twice. Okay, so we're given the second derivative, then we're given a condition about the first derivative, then a condition about the original function. Okay, so what we do is we want to get back to f, but we can't jump right from f prime back to f, so we have to go from f double prime back to f prime, and then take that back to f. Okay, so here's what we're going to do. We're going to start by trying to find f prime. So to get from f double prime back to f prime, we take the antiderivative. So the antiderivative of x cubed, the power pops up to 4, and then we divide by 4, minus, here the power pops up to 2, and we divide by 2. So 2 divided by 2 leaves us with technically just a 1 as a coefficient. And then we have a plus c. Okay, so that is our first derivative. Then they give us an initial condition for our first derivative. So we're going to plug that in as a first step. So if I plug in 1, we know I'm going to get 0. Okay, so my right-hand side, 1 to the 4th, of course, is just 1. So I have 1/4 minus 1 plus c, which is negative 3/4 plus c. So that means that c is 3/4. Okay, so we're going to take that and we're going to rewrite our first derivative. So f prime of x is now 1/4 x to the 4th minus x squared, but then instead of plus c, we're going to put plus 3/4 because we found the first initial condition. All right, now we're going to go from f prime back to f, and we're going to use that second initial condition. So f of x equals, we take the antiderivative here, power pops up to 5, and then we divide by 5, so this coefficient becomes 1/20th. Then minus, power pops up to 3, and we divide by 3. And then 3/4, its antiderivative is just a 3/4 x, and then we have another plus c. Now, if using the c in multiple places makes you uncomfortable, you can choose a different letter there, but it really doesn't matter because wherever you use it, it just represents an arbitrary constant. Okay? So now what we're going to do is we're going to plug in the second condition. So we're going to plug in 1 and set it equal to 2. So if I plug in 1, I get 1/20th minus 1/3 plus 3/4 plus c. Okay, so what I'm going to do, we're dealing with those fractions. We could convert them all to a common denominator of 60, but what I'm going to do is just plug them right into my calculator. So 1/20th minus 1/3 plus 3/4, that gives us 7/15. Okay, we could have done that by hand, but there's really no point. So 7/15 plus c. So what I'm going to do is I'm going to take 2, which is actually 30 over 15. And I'm going to subtract 7. So that means that c gives me 23 over 15. All right, so finally I'm going to plug it in. So f of x equals, I start with all this stuff and then tack on the constant that I just found. So 1/20th x to the 5th minus 1/3 x cubed plus 3/4 x. And then the constant that I just found, which is a beautiful 23/15. Oh, barely snuck it on there. It's not a very nice 3. Okay, so there we go. That is our function that has this as a second derivative and fits both of these conditions. If you plug 1 into the first derivative, you get 0. If you plug 1 into the original function, you get 2. All right, example 4 is another one of those particle motion problems. So let's take a look at this one. So now this one, we're kind of up to the second level here. So here, we just worked with the first derivative. Here we just worked with the first derivative. Then we moved to the second derivative. Now here we're back to talking about particle motion, but we're talking about the second derivative again. Okay, so particle is traveling at 72 meters per second. So that's an initial condition here. So what this says, this is the velocity. So what this says is that the velocity at t equals 1 is 72. That's an initial condition. So I'm going to write it down in kind of that function notation so it looks familiar to us. It begins to accelerate at this rate, that's our acceleration, until it stops. How far does the particle travel before stopping? Okay, so this is what we're going to solve here. So first of all, we've got our acceleration function. We're going to use that to come up with the velocity function, which will have a plus c, but then we're going to use this condition. So we take the antiderivative of this. So first of all, the negative 1/2 pops up to a positive 1/2, and then I divide by 1/2, which means I multiply by 2. So I have a negative 2 out front. Don't forget I have a negative right here. And then plus c. So that's my velocity function. So I'm going to plug in my initial condition. Okay, so I'm going to plug in the 1, set it equal to 72. Okay, so this just becomes a negative 2. And then plus c. Okay, so if I add 2 to both sides, that means c equals 74. So let's rewrite the velocity function. Okay, so what we're currently trying to solve for is how far does the particle travel before stopping? Okay, so here's the key thing right here. How far does the particle travel before stopping? So we want to know basically, when is it going to stop? How many seconds will pass by before it stops? Okay, so we are going to take this velocity function and we're going to set it equal to 0. Okay, because when the velocity is 0, that means that particle has stopped. So this is a little bit different than some of the other ones, kind of like a particle motion story problem. So we're going to add this term to both sides. Divide both sides by 2. And so when I divide both sides by 2, I end up with 37. And then to get t to the 1/2, because remember that's really the square root, so what I do is I square both sides. So when I take 37 and square it, I end up with 1,369. Okay, and this would be seconds. We could turn it into minutes if we want, but everything's in terms of seconds, so we might as well leave it. So that means that after 1,369 seconds, the particle stops. But more importantly, we're trying to figure out how far does the particle travel. Okay, so we want to know how far the particle has traveled after 1,369 seconds. Okay, so let's go with that. So I'm going to find my position function. So I'm going to take the antiderivative of this. So with this first piece, my power pops up to 3/2, and then I'm going to divide by 3/2, which means multiplying by 2/3. So I have a negative 4/3 out front. The antiderivative of 74 is 74t, and then don't forget my plus c. So now here's the part that gets a little bit weird with this one. Because with this one, we're not looking for a position function. We're looking for a specific position. So if we want to see how far it's gone from t equals 0 to t equals 1,369, it doesn't actually matter what the initial position is. So for our sake, we can just pretend that the initial position was 0. All right, because if I plug in 0, I'll get c. And then if I plug in 1369, I'll get whatever I get here plus c. So we might as well just knock off the c to begin with because we're answering a different type of question in this problem. All right, so I want to know what the position is at 1,369 seconds. Okay, this is a calculator problem for sure. Okay, so I've got a negative 4/3 out front. Then in parentheses, I have 1,369 raised to the 3/2 power, and then plus 74 times 1,369. Okay, so I get this lovely value right here. 101,306 divided by 3. Or approximately okay, and then that would be in meters. So you see what I'm saying here about leaving off this plus c, because say we said that the initial value was a 2, then at 0 the position would be 2, and then at 1369 the position would be 2 more, and we'd have to subtract them anyway. So we might as well assume that the particle started at 0 meters, and then we don't have to do any subtraction. Okay, so quite a while. It goes this far before it actually stops. All right, we've got a couple more on this back page. This one, the print for some reason on the AP problem came out really weird, so I'm glad that you guys have it nicely printed on yours. We've got one more of these, one more particle motion, the position, velocity, and acceleration problem, and then the AP problem is actually the same topic. This is a huge, huge, huge topic on the AP test. Always one of the free response problems is on particle motion, so we're going to get lots of practice here. So particle moves with a constant acceleration of 3 meters per second, so that's our acceleration function. At t equals 2, the velocity is negative 12, so we're going to set that up as one of our initial conditions. And the initial position is 1 meter. So initial position means the position at time t equals 0. Okay, so now this one, we want to find a position function. So very different from what we were doing with example 4. So here's our acceleration. So this means the acceleration is just a nice, neat 3. So that'll make it easy to take our further antiderivatives. So our velocity function. When we take the antiderivative of this, the antiderivative of 3 is 3t, and then don't forget you've got a plus c. We'll use this initial condition to solve for c right here. So if I plug in 2, I need to set it equal to a negative 12. So 6 plus c equals negative 12. That means that c equals a negative 18, so we can rewrite that velocity function. So 3t minus 18 is our velocity function. It has an acceleration of 3, and if I plug in 2, I get negative 12. So then I take the antiderivative again to get my general position function. Antiderivative of 3t squared is 3 halves t squared. I'm sorry, this isn't squared, this one is. And then minus 18t, of course, plus c. And then it says my initial position is 1. So if I plug in 0, then I should get 1. So plugging in 0 here, this would be 0, this would be 0. So that means that c equals 1. So let's rewrite one more time my position function. Okay, so there it is right there. That's the position function that we were looking for. All right, now this AP problem, it should be clear on your page at least, so I'm just going to read it off of my original copy. So a particle moves along the x-axis at any positive time, t is greater than 0. Its velocity is given by this very blurry function right here. It is a 4 minus 6t squared, so that I can actually see that. It's velocity. If the particle is at position x equals 7 at time t equals 1, so we can set that up as an initial positions. They use x as their position. So x of, oops, that shouldn't be a t, I guess that should be a 1. The position at 1 is 7. So we start with that. What is the position at t equals 2? So we have our velocity function. So we're going to use that to come up with a general position function. So we take the antiderivative. Antiderivative of 4 is 4t. Antiderivative of 6t squared is 2t cubed, and then you have a plus c. So we use this initial condition right here to solve for c. So we plug in 1, and we get 4 times 1 minus 2 times 1 cubed, and then plus c. We know that's supposed to equal 7. So 4 minus 2, that's 2, plus c is 7. So that means that c must be 5. So we rewrite our position function. Okay, so that's our official specific position function, not just the generic one. And then what they're asking us for is what's the position at t equals 2? So we are going to plug in 2 into our position function. Okay, so 4 times 2, of course, is 8, minus 2 times 2 cubed, 16, and then plus 5. So 8 minus 16 is negative 8, plus 5 gives us a negative 3, and even though it's hard to read, that would be option C. Now keep in mind with these, when they're multiple choice, there's no work required at all. So depending on what you could or couldn't do in your head, I guess, you could just circle an answer, and there's no work required, so you wouldn't lose any partial credit or anything. All right, so that's it for this one.